Right, good afternoon, everybody. Good afternoon. Oh gosh, it's been a long Thursday. Let's try again. Good afternoon, everybody. Good afternoon. That's much better. That's what I expect at Scifest Africa. Good afternoon to day 2. I can't believe we're already there. Welcome to this afternoon's lecture presented by Case Rijsdijk. Case, I'm going to be very honest. We did talk about this earlier, but this is the lecture that I actually kept for myself. The one lecture that I've kept for myself. It is a great privilege for me to act as chairperson for Case's lecture this afternoon. When I started at Scifest Africa in 2002, I was incredibly scared of this man. And Case, you know, over all these years, that healthy respect has continued, not only in me, but also in my staff. You know, when Case Rijsdijk phones, you know Case Rijsdijk's phoned. He is so a part of the history of this festival. Have you missed any, Case? No. So for the last 20 years, Case Rijsdijk has attended every single Scifest. He's a member of the advisory committee. I have learned so much from him, you know, that it really is, Case, it's a great privilege for me to stand here. And I want to say thank you very much for everything that you have done for Scifest Africa over the last 20 years, and for me personally, as media officer, as manager, as director. It's a great privilege. Thank you very much. Ladies and gentlemen, Case Rijsdijk, physicist, astronomer, studied at the Royal Observatory of South Africa, of the Cape. Switched on, thank you very much. Under renowned astronomers, then decided that really teaching physics and, you know, teaching young children about science, about astronomy, is his passion. And so after a long teaching career, both in South Africa and in, it was Rhodesia then, now Zimbabwe, came back to South Africa and worked at the South African Astronomical Observatory. He's been a pioneer in science communication in South Africa, specifically physics, specifically astronomy. Did you start the physics and the science and the astronomy and the physics Olympiad, Case? You did. Also the outreach program at the South African Astronomical Observatory. So, you know, he really is, in terms of science communication in South Africa, one of the leaders and a Scifest Africa legend. So, Case, also thank you for everything that you've done for science communication, for physics education, astronomy education in South Africa. And you know, really, it's when I started here as well, I didn't know much about science. I have a background in the arts, but it's become one of my passions. And really, what your involvement is one of the reasons why I'm moving to Square Kilometre Array. So thank you very much for the input that you've had. Welcome, and please tell us about telescopes as time machines.
Thank you very much. It's kind of humble and humiliating, but thank you. Can I move this out of the way? Before I start, I have an hourglass here. Now, you don't often see hourglasses this size, but this actually lasts for 1 hour. I was supposed to talk from 3 to 4, well, 3 to, and then some time for questions. So that's there, and you can see it. It's also, of course, on the screen there. So, quick overview of what we're going to be looking at is telescopes, what light is, the speed of sound and light, because we tend to don't understand really the history of this thing. We'll have a look at that briefly, and then we're looking back in time, and then of course we come to the Big Bang. We'll have a look at that quickly. How far back can we see? Other eyes, in other words, and this is a metaphor, as you'll see later on in the talk. And eventually, if you see that symbol there, that means time becomes a relevant issue. So what is light? Well, there is the visible spectrum. It's expanded into all the colors that we know so very well, but it's actually a small fraction of something we call the entire electromagnetic spectrum. So you've got high energy on this side, short wavelength light, and then long wave on this side. Radio waves, that's becoming a big issue in South Africa now with SCAR. But basically all this is light. We tend to think of light as the stuff that our eye can see, but in fact it covers the entire spectrum. And this leads to windows on the universe we can't, unfortunately, see the entire spectrum from Earth, because we're living in a planet where we have oxygen, we have gases in the atmosphere, as we couldn't live, but they obstruct. They cut out, thank goodness, all the high energy stuff, X-rays and gamma rays, that else we couldn't have life on Earth. And we have these windows, and you see there's a massive window here, and that's radio astronomy, which we're going to play a major role in South Africa here. But optical astronomy is a very narrow field. But originally, that's where everything started. That was the first window of the universe. Right? Galileo, and we'll see just now with his telescope, he looked at just a tiny little bit. In fact, that's an enlarged version or fraction of the whole thing. And of course, if we want to really see things, we put telescopes in space. Then we don't have to worry about the atmosphere, although technology now, we can subtract the atmosphere. But basically, these are our windows. So Galileo, this is Galileo's telescope. It was 26 millimeters. It's about an inch, about that big. A very small lens and very crude. But in 1610, when he first looked into the sky with his telescope, it was the first time that a new window on the universe was opened up. And it was a small, simple, and very crude experiment, but it changed the way that we looked at the universe forever. Today, telescopes, well, this is a sort of a 1900 type telescope. It uses lenses. They're very long, very cumbersome, but in its day, this was the best telescope we could get. And of course, they have a life, telescope life about 50 years. 1948, that's a 1.9 meter telescope at Sutherland, and it uses a mirror. It doesn't use lenses. And today, of course, good amateurs would use something like that. And with these sort of instruments, these instruments are usually about 20 to 30 centimeters in diameter, quite small, but they can do as much with modern technology as a 1 meter telescope could about 10 years ago. So you're finding now that amateurs are doing really fantastic work with small instruments. But of course, the ultimate is SALT in Sutherland, and I'm always criticized for showing this picture, because my colleagues say I must never show an observatory photograph with clouds, because that's not a good thing. But anyway, that's SALT in Sutherland, and it's a wonderful instrument, and it's really beginning to show its value now. And in space, we've got Hubble, and we'll see some Hubble images later on. Hubble has revolutionized the way we see the universe. It's revolutionized astronomy. People become aware through Hubble of an amazing work that astronomers do, and that Hubble is responsible for a huge amount of that. Nowadays, we have other telescopes like Kepler, and we hear Professor Eric Wilcox later, and he's going to talk about what Kepler does. Kepler looks for extrasolar planets around distant stars, and you'll learn more about that. So these telescopes are outside the Earth's atmosphere, so therefore they can see things a bit better than we can from the Earth. Now, telescopes collect light. And what can we do with it? We've collected the stuff, and then what do you do? Well, there's only three things you can do. You can take pictures, make images, which is very popular. You can measure the amount of light that a source is giving. It's called photometry. And then you can do spectroscopy. In other words, you take the light, you split it up, and you find out what's actually there, how hot or cold things are, and so on and so forth. So spectroscopy is very science. We're not going to look at the last two. We're just going to look at, we can take images, because that's what our eye sees. We see each other because we have an image. Our eyes form an image on the back of our eye, and we can see and so on. And that's what the first telescopes did. So we were talking about looking, we're talking about images. So Galileo, when he first looked at Jupiter, he saw this thing, and he saw those four objects there. He looked the following night, and he saw that. And of course, in those days, you couldn't take pictures. You had to draw everything. So he would sit at his telescope and draw what he saw. And here's Saturn. He didn't know it. Well, he knew it was Saturn, but he didn't know what it was. Because you can see here that there's definitely a ring-like structure, but here and here, they're not really rings. I don't think he knew what he was looking at. But he did do some very detailed pictures of the moon, and they're really quite interesting. And he wondered what the craters were, and of course, today we know a lot more about the moon. Then there was Lowell, Percival Lowell. Now, I put him in here because his story is very interesting. He looked at Mars. Lyell was a man who put a lot of money into astronomy, and he built a very large telescope, and he studied Mars. His passion was Mars. And the unfortunate thing about it was he discovered the canals on Mars. And we now know that what Lyell was looking at was his optics were not coated. So in other words, they were just, no coat, just well-shaped lenses, but no coating. So there were reflections. And in fact, what he was looking at were the veins in the back of his eye. Right? And it's so sad that he did that, because he thought really that he was seeing these canals. And of course, we know nowadays that there aren't any canals. And it's just as well that he's not around to find his massive disappointment. It must have been hugely disappointing for him had he known, but he didn't. So we suspect that these are the veins in the back of his eye due to reflection from the bright light being reflected back into his eye, and so on. So, but we can take some wonderful pictures. I'm not going to give you a picture show here, but there are some beautiful pictures. I like this one. It's almost cathedral-like in its beauty. And what's happened here is that these stars here have formed. They've used up their surrounding gas and stuff. And here you can see this star here is carving out a large hollow inside this massive cloud of stuff. And it's a beautiful, beautiful Hubble image, absolutely stunning. And so is this. And you can go onto the internet, and for those of you who want to, go to Google, type in APOD, A-P-O-D, and you get the astronomy picture of the day. And every day you get a different picture, and they are absolutely beautiful. By amateurs from all around the world, you can look at the archive too. So that's one thing you can do. Now, to get to some serious business now, in the past, it was thought that light was instantaneous. So if I shone a torch, the light got to where it was going the same time I turned it on. And we knew that, well, we thought we knew that, because every time we saw a flash of lightning, you waited and then you heard the sound later on. Okay? So, but how far away was the sound? How do you measure that? So they assumed the speed of light was infinite. So, if you were standing somewhere and you saw a flash of lightning and started counting, and 1, and 2, and 3, and you hear the thunder, then it's 3 seconds from where you are standing to hear from the light flash. It's 1 kilometer away. So every 3 seconds you count 1 and 2 and 3 and 4. If you divide that by 3, it gives you the number of kilometers that the sound of the flash of lightning is away. And I use that often when I'm at home, because if I get a thunderstorm, I want to disconnect my computer before it gets fried. So I can count mentally in my mind if the thunder's coming closer or going away. So there we go. But they thought that the speed of light was infinite. And they tried. And you can try this. You can do this as kids. You can try this at school. If you clap your hands in front of a large building, you'll hear an echo. And if you time your next clap with the echo and repeat that repeatedly like this, all right, then you can count the number of claps you have in a certain time. And then you know how long it took to get the sound from there to there and back. You divide that out, you work out the speed of sound. It's a very simple experiment you can do anywhere you like, and you should get a speed of about 330 meters per second. So that's the way you can measure the speed of sound. They tried to do the same thing for light. Over the years, Galileo, scientists for years and years and years and years tried to measure the speed of light, and they failed. They tried similar experiments as you do with sound. They tried with mirrors and flashing lights, firing cannon, and all sorts of other things. And here's sort of an animation. You flash a light hilltop to hilltop. They could never measure the time between the two flashes and the reflection and everything else. So as far as everywhere is concerned, light was infinite speed. And the first measurement that we knew that light wasn't infinite was Roman in 1676 rather. He used a telescope very similar to Galileo's, and he looked at Jupiter. But he looked at Jupiter for a long, long time, and he realized that the moons orbiting Jupiter would go behind Jupiter and then reappear. And he would do that, and he did that for a very, very long time. And then he realized that when the Earth was there relative to Jupiter, it took less time for the thing to disappear than when it was there. And the only thing that he knew the orbit was fixed, he couldn't change that. So the only thing that he thought would change was the speed of light. It wasn't infinite, it took time. And his estimate was not great, 60%, he was 66 close to the short of the mark. Well, it's 33% short of the mark. But the point about it was, what was important, it had a finite, it was finite. It wasn't infinite. So, you now have light travel time, and there's the hourglass. If you know the distance to a light source that's very far away, because let's face it, light travels at 300,000 kilometers per second. To put that into perspective, it's 8 times around the world in 1 second. Okay? So you can't sort of, that's why you can't just quickly measure the speed of light. But if you look at the moon or a star or the sun or whatever it is, and you can work out the time it takes for light to reach you if you know how far away it is. So for example, the moon to the earth is about 1.25 seconds. The sun to earth is about 8.5 minutes. The nearest star to us, Proxima Centauri, and last year was the 100th anniversary of its discovery, Proxima Centauri, 4.25 years about. So what this actually means is that you're seeing the moon the way it was 1.25 seconds ago. You're seeing the sun as it was 8.5 minutes ago, and Proxima Centauri as it was 4.25 years ago. So in other words, what you're seeing now is actually history, because that's the time it took light to get to you. So you're looking back in time. So a galaxy, for example, that's 10 million light years away from us. The light would take 10 million years to get to us. So what you're seeing now is an image that's actually 10 million years old. It is the actual object. The image is new, but the object is 10 million years older than it is now. So we're looking back, constantly looking back in time. Now this is a beautiful picture of our twin galaxy. Is it possible to turn the lights down a bit here? Because the images are very beautiful, but we can't really see them nicely. Okay, well, we just carry on. Thank you. Okay, is everybody happy with that? Anyway, that's the Andromeda Galaxy. It's our twin. Our galaxy is very similar to that one, but this one is a lot further away. So in fact, when light left the Andromeda Galaxy, family Ples was walking on Earth. Right? So the time that it took the light to get from Andromeda to Earth was 2.3 million years. So what we've got now is, we've got her skull. And you can look at this afterwards. Okay, this is Mrs. Ples. Well, it's actually Master Ples now, I believe. But the point is that it took 2.3 million years. So we're looking back in time. So the Andromeda Galaxy is in fact 2.3 million years. What we're seeing now is 2.3 million years old. And we do this with a lot of fossils. If you ever get a chance to go to Sutherland, there's a whole exhibit there of fossils and stars. It's beautiful. Dave Laney and I built this up over the years. And one of them is Eve's footprint. About 117,000 years ago, a girl ran onto the beach in the Western Cape. And at that time, the light left the Large Magellanic Cloud. We'll come back to this cloud later on. And all we've got now is the fossil footprints. So that's the youngest link that we have with the stars, the fossil link. And then you can go back 2.2 or 0.2 billion years. That there's a picture of the Vredefort Dome. It's an impact crater in the Free State. It's the largest and oldest impact crater on Earth. It's over 300 kilometers in diameter. And when the impact took place, we now pick up what we call fracture cones. And I've got some examples here you can have a look at afterwards. So when the impact occurred, the rocks were so shocked that the whole structure changed with the shock wave. And you've got these fracture lines like this. So that was 2.02. So these rocks, when you pick up this rock, you're holding something in your hand that is 2.3 billion years old or more. All right? It's quite sort of an amazing thing. So that there is the object. When the light left there, the impact occurred on Earth 2.3 billion or 2.02 years ago. So there we go. But how far back can we see? Well, we'd like to go right back to the beginning, which is the beginning of the Big Bang. That's 13.7 odd billion years ago. And that it's difficult to look right back to the beginning, because right at the time of the Big Bang, there was no light. There was what we call a particle soup, and there were no radio waves, anything from the electromagnetic spectrum wasn't there. But the question then comes, well, what was there before that? So we have to have a look at the Big Bang. We'll do that now because I think it's important that we understand why we want to look back in time, and then later when we finish up, there's a good reason for it. There's a misconception about this. The first misconception is that it didn't expand into anything. It wasn't like setting off a firecracker in this room and watching the gases expand into the space of this room. What actually happened was that whatever it was expanded. But these images that you often see to explain the Big Bang, inflation and the whole timeline and everything else, are very good to explain things, but they're very misleading because they give misconceptions that the universe is expanding into something, and it's not doing that. Right? So here's another view, and this is my attempt to explain this. The first thing is, can you see the little dot there? Let's imagine that you've got this tiny, tiny dot, which is extremely, extremely hot, very, very massive, very, very dense, and please don't ask what happened there before that. All right, we'll start with that. And that expanded and cooled. And it expanded and cooled. And it expanded and cooled. It expanded and cooled, and it expanded and cooled. And this is where we are today. We're right in there. Okay? So it's not expanded into anything, that the entire space that we exist in has been expanding for all these years. And so effectively, that there is the same as the outside, well, the same as that blob there. This here is the same as that, right? It's expanded. It's now larger than it was before. And this is now the look-back time, so we can look back. Well, we'd like to look back to there, and that, of course, is looking back to there. If you can see there, you can actually look back to there. And that's what we're trying to do. But it's very difficult because, as I said, there was no light. Now, this is a wonderful illustration from NASA. It's the best diagram that I've seen, and I think NASA's done a brilliant job here. That they've got this here, and you can see here that there is the Big Bang. It's the same as I pointed out just now. Then we're going to look at the Hubble Deep Field and the Hubble Ultra Deep Field, and we would like to look, these are the first stars, that was when the first stars formed. We'd like to look back to there, and eventually to there. But we can't do that with optical telescopes. We'll come to that just now. So let's first have a look at Hubble Deep Field. This was an exposure that took over 100 hours of Hubble time in 1995. And it covers the size of if you have a match in your hand, the head of the match covers that area. And in that image, there are over 3,000 objects. Okay? Then in 2004, they had a 1 million second exposure for the Hubble Ultra Deep Field. It saw 10,000 objects, 13 billion light years away from us. So we're looking back into the past to about 700,000 years after the Big Bang, which is phenomenal. And then recently we have the Hubble Extremely Deep Field, which added another 5,500 images with a 2 million second exposure. And there it is. That's the Hubble Extremely Deep Field. It contains over 15,000 images in that same match head area. Okay, but you're looking back to around about 500 at least 500 million years after the Big Bang. So that's an amazing achievement. But the look back time. Now here's the thing, that's the present. We can see these things like our local galaxy is in this region here. And as you go further and further back, right, we can actually see right back to there, and now we can look back to the cosmic microwave background. That's the first light that we saw. We can't see with an optical telescope beyond that because there was no light. So we need to find out how do we look beyond that. So SCAR can't do that, but SCAR will, and I think this is a beautiful image. This is actually an image of the first telescope that was opened last year. It was launched, and there's the Milky Way. there's the Large Magellanic Cloud, and there's the Small Magellanic Cloud. It's a beautiful picture. It really is sort of an iconic image of sky. And it can see further back than HST, because it looks into much longer wavelengths, and in more detail. But it cannot look behind that last barrier. So what we're looking at up to now is optical telescopes, things that we use that look at electromagnetic radiation. But shortly after the Big Bang, as I said before, there was no light. It was opaque. Light broke out of this what we call particle soup, or the universe became transparent about 380,000 years after the Big Bang. So if we want to look back beyond that, we need to have a different way of doing it. And this is one way we can do it. We can use different, and I'll put telescopes into inverted commas because these are not telescopes. These are just detectors, would be a better term to use. They detect different things. And they're very large and expensive. Now, neutrinos and gravitational waves are one, and then particle physics is the other one. Fundamental particles can actually go right back to the very, very beginning. So what are neutrinos? These are tiny, tiny subatomic particles that were predicted in the 1930s. They were the actual first detection of naturally occurring neutrinos was in South Africa in a deep gold mine, 5,000 meters down, and they discovered neutrinos. They come from deep inside very powerful energetic explosions. The sun, for example, produces billions. Whilst we're sitting here, every single second, there are billions and billions and billions of neutrinos going straight through you. Neutrinos act with virtually nothing, right? They just don't interact. Light interacts with everything, which is why I can see you. But neutrinos don't interact. So they were first detected or related to astronomy in 1987 when a star exploded in a Large Magellanic Cloud called a supernova. And at the same time, neutrinos appeared. They were detected. Not many, I think about 11, but it was the beginning of neutrino astronomy. And neutrinos, this is an image of the sun of 500 days of collecting data. But neutrinos, there are many observatories nowadays to pick these things up, but neutrinos, this is one of them. They can see back the long way. We'll come back to that now. This is IceCube. This is a device in the South Pole. There is the Eiffel Tower in Paris. So what they do there is they have steam, and they drill a hole with the steam in the ice. And as the ice melts, it's followed by a long cable which has got photomultiplier tubes attached to it. And as they go down, they get frozen in when it eventually the whole thing is complete. So they've got all these, you can see these are very, very long chains, and they built a whole thing. It's called IceCube. It's a cubic kilometer of photomultiplier tubes. And what happens is, here's an animation. You can see here comes a neutrino. It can probably leave a trail behind, and by analyzing all this stuff, you can figure out the energy and where it came from. And all these detectors around the world that I mentioned before are opening up this other window called neutrino astronomy. That's happening today. And they are enabling us to look back to here. We can now see way back past the Dark Ages if we can get sufficient data about what happened with neutrinos. So that's a very active field of research today. Gravitational waves were in the news very recently. They were predicted by Einstein 100 years ago from a general theory of relativity. And he said, he recognized that it would be very difficult to detect because the waves would be very weak when they got here. And he was quite right. It's taken us until the 16th of February this year to make the first confirmed detection of gravitational waves. And that is a really major step forward. They were detected by two detectors in Washington State. And it opened up a whole new window into the universe. So here we have the detectors. These are 4-kilometer long arms. And as the gravitational wave passes through those things, they will change the length very slightly. Right? And because they detected this signal in two different observatories the right time apart, that was the same gravitational wave. So therefore, we can confirm that this was actually a gravitational wave. So that's the newest window onto the universe that's been opened up. And in time, no doubt, we'll be able to get better instruments to actually look at gravitation. As one of these is being built to be launched into space. It's a European Space Agency exercise, but the arms are 5,000 kilometers long. So there'll be phenomenal advance in our sensitivity. Here's an animation of what caused that thing. This is two black holes rotating around each other. And you'll see as they merge, they will start radiating, because of the collapse, they'll start radiating out gravitational waves. That's the red stuff that's coming out now. Okay, and you can see there they now merge, blob into one, and they burst and out goes the gravitational waves. And these are what we picked up. This was the event of two, you can see there the red waves going out from the black hole. For now, a single black hole. So that's the cause of those gravitational waves. So gravitational waves can see back right to the beginning. If we can actually interpret the data and collect the data, we could actually try and figure out the Big Bang itself, which is a fantastic advance. Fundamental particles, if we understand the basic building blocks of matter, or what nature are, then we can create models, like the Big Bang model, for example, and they can be tested and verified. Now, the collider, like the Large Hadron Collider in Switzerland or France, discovered the Higgs boson in 2012, as we all, big news at the time. But basically, the Large Hadron Collider can reproduce the conditions, or similar conditions, of the Big Bang inside that machine. Which means that we can look at the stuff that was around when the Big Bang actually occurred. The quarks and gluons and things like that. We're not going to go into that. It's a very complicated and technical subject, but LHC can do that. So here's another one of the sort of Big Bang models, which I said treat with caution, but will the Large Hadron Collider explain what we're seeing today by explaining what happened, what happened there? Okay? So if we can explain what happens there, we can understand what happens this. So that's, in a way, LHC is looking back. So by recreating the Big Bang conditions, right, we are actually looking back over 13 billion years. So the model needs testing. We have the Big Bang model. It's the model that we have. It fits the data. It's the best model we have. It does not mean it is correct. Right? There are a lot of people, a lot of scientists who have different views on this, but basically this is the best model we have. So until we get something better, we'll work with this one. So here's the thing I have of the cosmic egg. It comes from a poster from the University of Cape Town some years ago, but it explains basically that to complete the cosmic egg up there, we need to do this by actually studying the universe at large. And we can do that. We use telescopes to study this region here, which if you imagine people being here, then you get bigger and bigger and bigger as you go along. And eventually, in order to explain the really big stuff, you need to explain the small stuff from this side. So going smaller and smaller and smaller, right? To quarks, to preons. And we're now sort of looking at this area here with string theory and all sorts of other things. So hopefully we'll get some answers there in the future. Time machines, I'm not sure whether IceCube or the Large Hadron Collider or LIGO and these sort of things, whether we can class those as telescopes. Because I put them into telescope category because they're allowing us to see, in inverted commas, back further in time. And they're all time machines. And the new windows opened up by neutrinos, gravitational waves, and particles allow us to better understand the universe. So, we don't really want to use one of these. Okay? We'd rather use some data. But of course, you can't collect data of the future. So what you can do is you can, if we better understand the past, we are better able to extrapolate the current data that we have into the future. So we can get a better image of what the future may well be. And that's the only way we can do that. So to get a glimpse of the future is to make better and better time machines. That's the only way we're going to actually understand where we're going. So I'll leave it there. Thank you very much for your time. And I haven't done too badly with my time clock there. So thank you very much. Any questions? I'm more than happy to answer. Yes. Yes.
Yes, gravitational waves, and now we've established that they actually do exist, and not just Einstein's theory. I mean, how exactly are we going to use them? Because I know these two, when they actually found them in Texas or whatever.
Yeah.
I mean, how exactly is it going to work that we can actually go further on from that? Without having
You mean how do gravitational waves work?
I mean, are we going to continue to look at them or what? Well, I mean,
Well, you don't look at them. You collect the data and you interpret. One has to get used to the fact that we are used to looking through a telescope and seeing a picture, seeing an image. If you look at a radio telescope, you get a whole pile of squiggles and stuff on a piece of paper or on a TV screen or a computer screen, right? But you can reinterpret that data and make an image out of it. If you have enough data about gravitational waves, you're able to do a similar sort of thing, right? But it tells us the mechanisms that cause these waves. And that's what we really need to know. What causes the waves?
Okay.
And that tells us we don't need a picture of it.
No.
We need to understand the causes, right? And from where they came. Now that's the big problem at the moment. We can detect the waves, but we can't really pinpoint where they're coming from. Our instrumentation is too crude. We need to wait for more advanced technologies and techniques to actually pinpoint that this particular gravitational wave came from that particular place in the universe.
So we'll have to actually start building.
Well, they are building LISA, which is the Laser Interferometer Space Observatory. They've had the first successful test. They've got two little cubes that they're floating freely in space now, and they're going to then, get them stabilized, get the laser to bounce off them, and so on. But they need two arms of that, but they're 5,000 kilometers long.
Yeah.
So, that's the next stage.
Yeah, exciting.
Yes.
I like the image that you had of the beginning of the universe being a period and then it got bigger and bigger. Well, at the end you showed like a star and it was in the middle of...
Yeah.
So where are we
Okay.
in the universe?
It's one of the big problems we have, because you say, are we in the middle? Because if something is infinitely large, there's never a middle. There can't be a middle. But the best analogy I have that I can think of, and you have to take one dimension down, if you imagine a balloon and you stick some jolly dots on it. People always say mark it with a Koki pen, but then the Koki dots expand too, which isn't true. Stick some jolly dots on the balloon, then blow the balloon up. And no matter which dot you look at, all the other dots are moving away from it. So you take that up one more dimension, whichever way we look, everything is moving away from us. Okay? So we're not at the center, but, wherever we are, everything else is moving away from us. Like, we've got bad body odor or something, it was running away from us. But no matter where you go in the universe, the picture is the same. Everything's moving away from everything else.
Even if you're at the edge?
Well, there is no edge. Okay, that's the whole big idea. When I draw a picture there, it's actually 2 dimensions trying to explain 4, which is kind of tough. All right, there is no edge. As late Tony Farrell said, when somebody asked him, well, what's beyond that? He says, chocolate. And he says, prove me wrong. Okay, we don't know. And I know, people like Roger Penrose talk about something called the ectoparodic universe. Now, the universe before the Big Bang. All right? And then you move into multiverses and cyclic universe and all the other sort of stuff. There's no data. So as a scientist, I'll stick with the models to have data that we can confirm and check and balance out. So that's where we are. But there is no center to, I'll put it there because if I put it somewhere else, I'm going to get even more difficult question to answer. Okay? So that's what that one is. Anything else? Yes?
Thanks for the talk. I just have one question. You're basically explaining the expansion of the universe.
Yeah.
In that we're not expanding into anything.
Correct.
So then is it safe to say that the universe is continuously making space and time?
In a way, yes. well, we now know that the universe is expanding at an accelerating rate due to something called dark energy. All right? But we're just creating more space at a higher rate. And of course, with that comes time, because you've got to look back to get there. Oh. Anything else?
Well, who's working on dark energy at the moment? Then?
Sorry?
That's a bit, who's doing the work on dark energy? Because we're into quantum physics.
Well, I haven't got an encyclopedic list, but I can tell you it isn't an encyclopedic list of people who are trying to figure out what it is.
Yeah.
I have some views on that, but we won't go down that road just yet.
You don't often see much reported about it, do you?
Sorry?
You don't often read much of what's being reported about it.
Well, there's a huge amount written about it, but it's kind of technical and tough stuff. You get involved with arguments with guys called string theorists and loop quantum gravity people and these sort of things. You don't want to get involved with those. Yeah, yeah. Yes?
For the young people here who might be considering a career in astronomy, what do you do all day long?
I don't sit in front of a telescope and look at the night sky all day. I'm a theoretician, basically, but an ordinary astronomer would normally go through the normal academic training career. University, at school you do maths and physics and stuff. University you do maths and physics. And then later on you study more and more, you get a PhD and you become an astronomer. And then what you then do is you have an idea, you want to investigate it, you go and collect data. So you go to an observatory, you ask for time, you get given time, and you spend a week or 2 weeks at an observatory, you collect your data at night, so you're working at night and sleeping during the day, and then you come back to your office in the observatory or university, wherever you are, and you sit down and try and figure out what you've collected. And you write a paper about it and create a model and discuss it with colleagues. And basically, it's a great career. You meet wonderful people. You do an enormous amount of travel because there are lots and lots of conferences you go to. So you see the world, you meet wonderful people, and you interchange ideas. And as you get progressively more and more into the field, you become more specialized. And yeah, it's a fantastic career, but it's not something that suits everybody. It requires commitment, passion, and dedication. And that's about it. But it's a wonderful opportunity. And today in South Africa, I think the youngsters are very privileged in that they have an incredible opportunity with SCAR, with SALT, and other instruments like HESS in Namibia. And we cover the entire spectrum now in southwestern Africa. It will become, the Southwestern Cape will become the biggest science hub in the planet. Bigger than LHC, bigger than anything that's ever been done before. And the amount of data we collect is unbelievable. So the future for the youth is fantastic. But do your physics and your science at school. Yeah. Sure. Yeah, absolutely. Yes, sir.
With the movement of technology at such an exponential rate, the space industry obviously is changing rapidly. Private enterprises coming in. It also means that there's a large space for citizen science to be involved in observing the universe. What are your views on that?
Well, I think it's a fantastic opportunity for the public to get involved in real science. There's Galaxy Zoo is one. There's a couple of others. You can just Google them on the internet. But it means you've got to commit yourself to doing that on a regular basis. And that's one of the problems with all these exercises is commitment, and passion. Yeah. But it's there. The opportunity is there for everybody. Any more? Yeah, I'm happy to talk to people. Come and have a look, please, at the rock samples and master plays, for those who want to. So thank you very much.